Pluto is a distant and mysterious dwarf planet which was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen? And what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon? Or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag of a possible hazardous collision between these two planets that could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of space mechanics. The three-body problem in space involves figuring out how three objects like Pluto, Neptune, and the Sun move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complex way. The terms as aethal libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is as aethal libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zlee, Leff, and Kai, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, VZK helps us understand why its path around the Sun is so unusual, even though Pluto's path seems all over the place. This oscillation helps keep it moving smoothly for a long time. The VZK oscillation shows that even if things in space seem wild and random, some patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, making sure it doesn't crash into Neptune or get thrown off course. This three-body problem helps in understanding how these paths change because of the way these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the big planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 rounds Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady, but Neptune isn't the only one helping. Jupiter's gravity also plays a big part in keeping Pluto's orbit safe and stable, and Saturn helps a bit too. These tests show that Jupiter's gravity alone is strong enough to make sure Pluto stays on a stable path for a really long time, even billions of years. So, it's like Neptune, Jupiter, and Saturn are all working together to make sure Pluto keeps moving safely in space without running into trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto ESP, especially with talks about it possibly crashing into Neptune in the future, understanding its orbit is really important. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to grasp our place in the universe better. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly change its long-term orbit. Using computer simulations has been super helpful for scientists to figure out how Pluto moves in space. These simulations use tricky math to mimic how Pluto and other space objects like Neptune pull on each other. By changing little details in the simulations, astronomers can see how even small tweaks can make a big difference in where Pluto goes. Back in the late 1980s, these simulations showed something really interesting about Pluto's path. Even though it has things like azimuthal and latitude libration to keep it steady, its orbit can still be pretty wild and unpredictable if you start off with just a tiny difference in where Pluto is or how fast it's moving. Over many years, its path can end up looking really different, but even with all this chaos, Pluto's orbit stays stable for long periods. Pluto's journey around the Sun may seem chaotic, but it actually has an underlying order that keeps it stable for billions of years. Predicting cosmic events, especially for orbits like Pluto's, is challenging due to the unpredictability of such systems. Numerical simulations help in forecasting the paths of celestial bodies, but they also highlight the limits of our predictive capabilities. These models depend on precise initial conditions, and any minor error can lead to vastly different results. This unpredictability reminds us of how much remains unknown about the universe. Despite significant strides in understanding space, the gravitational influence of giant planets on Pluto provides valuable insights into the broader dynamics of the solar system, showing how planets can affect the stability and trajectory of other celestial bodies. Major astrophysicists like Neil deGrasse Tyson are now raising concerns about a potential collision between Pluto and Neptune. Tyson, known for his role in reclassifying Pluto as a dwarf planet, emphasizes how evolving knowledge in astronomy can reveal new dangers, such as Pluto's unpredictable orbit. He highlights the importance of public engagement in understanding these cosmic events and stresses how a collision could have catastrophic consequences, potentially altering the universe's balance and affecting Earth. Michio Kaku, a theoretical physicist, also weighs in on the debate. Linking Pluto's orbit to his work in string theory, he believes studying celestial mechanics like Pluto's gravitational interactions with Neptune offers insights into the universe's fundamental laws. Both Tyson and Kaku see the potential collision as an opportunity to observe unprecedented astrophysical events that could provide crucial data for theoretical physics. If Pluto and Neptune were to collide, It would release an immense amount of energy, likely shattering Pluto and creating debris that could spread through the solar system, posing hazards to other planets and their moons. The collision could alter Neptune's orbit and atmosphere, producing conditions that might help scientists test predictions from string theory and gain new insights into the fundamental nature of the universe. Although Earth might not experience a direct impact, the scientific implications would be profound. The stability and chaos of Pluto's orbit highlight the complexities of celestial mechanics. While catastrophic planetary collisions are rare, they cannot be entirely ruled out. The dynamic nature of planetary orbits, influenced by gravitational interactions, points to other potential cosmic events. For example, systems like TRAPPIST-1, where multiple planets exist in close proximity, have the potential for orbital resonances that could lead to instability. Scientists closely study such systems to better understand planetary movement and the possibility of future collisions. Furthermore, rogue planets, which drift through space after being ejected from their star systems, add an additional layer of unpredictability to the cosmic landscape. Over time, rogue planets drifting through space can travel vast distances, potentially entering regions far from their point of origin. During their lonely journey, they carry the potential to cross paths with other star systems. If one of these wandering planets enters another solar system, there's a small chance it could collide with a planet in that system. However, space is incredibly vast and mostly empty, making the odds of a rogue planet directly hitting another planet very slim. The sheer scale of interstellar distances and the relative rarity of planets in open space act as buffers against frequent collisions. Additionally, rogue planets are uncommon compared to the number of stars and planets in stable orbits, making such encounters even more unlikely. In cases where galaxies merge, their respective star systems can be thrown into disarray. The vast interstellar distances make it improbable for planets to collide directly during these cosmic events. However, the immense gravitational forces at play dramatically alter the orbits of stars and planets within the merging galaxies. This turmoil can lead to planets being violently ejected into the cold, dark expanses of intergalactic space, becoming rogue worlds untethered to any star. Alternatively, these gravitational disruptions could lead to scenarios where planets are ejected from their orbits, collide with each other, or crash into their host stars. In some cases, the gravitational reshuffling can even trigger the formation of new celestial bodies or lead to the ignition of new stars as gas and dust are compressed under extreme conditions. In our own solar system, theories about the late heavy bombardment suggest that a period of increased comet and asteroid collisions occurred due to gravitational disturbances from the outer planets. This phenomenon, believed to have taken place approximately 4 billion years ago, indicates a time when the solar system was much more chaotic and violent. The gravitational disturbances are thought to have been caused by the migration of the gas giants, which disrupted the orbits of numerous smaller bodies in the Kuiper belt and asteroid belt. As these objects were thrown into erratic paths, many found their way into the inner solar system, leading to a spike in impacts on the terrestrial planets, including Earth. While not involving planet-on-planet collisions, this demonstrates how gravitational interactions can lead to significant changes in celestial bodies' trajectories. This bombardment likely played a crucial role in shaping the surfaces and geological histories of these planets, including the potential delivery of water and organic materials to Earth. Over the long term, as stars evolve and lose mass, the orbits of planets can expand and potentially intersect. This process is particularly evident in systems where stars end their life cycle. As a star ages and burns through its nuclear fuel, it often undergoes significant changes in mass, especially during stages like the red giant phase or when shedding material in a planetary nebula. These changes in stellar mass can dramatically affect the system's gravitational balance, causing the orbits of surrounding planets to drift outward or become more compact. This is more likely in multi-star systems, where complex gravitational interactions can lead to unstable orbits more easily. In such systems, the gravitational pull from multiple stars can interact unpredictably, worsening the orbital shifts and increasing the likelihood of orbital crossings. This can lead to scenarios where planets may be captured by another star in the system, collide with other bodies, or be ejected into interstellar space. In all these scenarios, the actual occurrence of a planet collision is still considered highly unlikely. The vastness of space and the relative smallness of celestial bodies make direct collisions rare events. However, these possibilities are of great interest to astronomers and astrophysicists, as they provide insights into the dynamics of planetary systems and the evolution of galaxies. The study of Pluto's orbit represents the continuous quest for knowledge and understanding in the field of space exploration. As Tyson and Kaku have shown, every discovery and every piece of new knowledge brings us closer to unraveling the complex nature of our universe. It's a journey that challenges our perceptions, expands our horizons, and inspires future generations of explorers and scientists. This constant observation can help us predict major catastrophic events that might occur in the future, such as the collision of Pluto and Neptune. Thanks for exploring with us these revelations. Click now on the next video that pops up on your screen. It's unbelievable.